Good morning. It's good to see all of you. Thank you to Susie and to the steering committee for asking me to give this talk on the call to action. I figured out that they probably gave me the job because I would do the least amount of damage here. So Margaret Maternity, who was an assistant director for sites at NSF, gave this talk in 2022. And she said, research is planting trees now in order to have shades or fruit in the future. I think of it as doing this for our grandchildren. I just spent this past weekend with my 3-year-old and 1-year-old grandchildren. And every time I look at them and I think about the research that we do, I say, well, the work that we do might not benefit our generation, but it'll definitely, or hopefully, will benefit their generation. So that's how I think about research in quantum computing. So I want to begin by showing you a chart that many of you may have seen in other contexts. But this is about how computers and processors have changed their performance, have improved their performance over a period of about 40 years or plus or so, beginning about 1970 and ending around 2015 or something like that, right? And you can see clearly 3 different generations: the CISC generation, which is complex instruction set generation, RISC, the reduced instruction set architecture generation, and then this multi-core generation. And what is being plotted on a logarithmic scale, you can see things are going up by a factor of 10, is the number of transistors on a chip, and you can see that number is going in millions, in thousands. So it goes from about 10 to the 0 to 10 to the 7 in the scale of thousands of transistors. And you can see that's kind of been increasing for all this time, and that's called Moore's law. And that also is kind of coming to an end right now because you can't get transistors smaller than a few atoms, right? So it's kind of hard to make them any smaller. But you can see the other trends are actually more troubling. So the trend for example, this is the performance of the computer processors that are on your laptops and on the desktops, on the machines that we use. And you can see that's kind of increased initially exponentially and then sort of has plateaued. And basically, it's not increasing very much anymore. And those increases now have come through changes in architecture. So from going from a very complex set of instructions, the instructions that the processors actually to perform to do the kind of tasks that we ask them to do, to a very clean design that gives you a very small set of instructions organized in a very careful way such that getting the data from the memory into the registers and so on is just a separate operation. The operations themselves that they work on the data is a separate operation, and all of this is kept in a clean orthogonal design, but also in a simple way so that you can get good performance. So we benefited from that in the 1990s and 2000s and so on. But you can see that once the transistors got small enough, you couldn't increase the frequency to get better performance because of for power constraints that you have. There are small leakage currents and things like that. And that means that you can't really increase the frequency and get better performance that way. And so in that generation, architects started putting in more cores. So using transistors, but using more computing units, and then using parallelism to get better performance. But you can see that all of that is sort of plateauing out. We're kind of coming to a point where if our grandchildren want to enjoy the computing performance that we enjoyed, where the performance was doubling every 18 months, if our grandchildren need to enjoy that, that's going to have to come from a different source. Okay? So computer architecture, as Hennessy and Patterson, who won the Turing Award for their work on designing the RISC architecture, calls us a new golden age. So it's a time when we have to think about new ideas. So what we need is a leap. And this is a quantum leap, or I'm saying this is one possibility of trying to get good performance using quantum machines. So I don't know what color quantum computing is. But any case, here are two quantum computers. So this is the IBM machine, and again, I'm not making a case for any particular company or the other. But here's another one, D-Wave, that uses a different sort of idea. So use of a quantum implementation of simulated annealing, which some of you may know, or many of you might know about. So it uses, it solves all the optimization problems. So only optimization problems that can be solved, formulated in a particular way as quadratic unconstrained binary optimization problems and so on. But the idea is that these things are computed. These machines are now computing not with transistors and so on, but with electrons and photons and atoms that are charged or may not be charged and so on. But these are entities that are at that scale that they obey the laws of quantum mechanics, and so that's what we need to understand in order to compute with these things. So I just want to point out very quickly, give you a little context. So I'm not giving you a historical talk, but I do want to point out two people. So Jeff, where are you? Okay, great. Did you know Paul Benioff? Okay, all right. So Paul Benioff was at Argonne National Lab. Fortunately, he passed away a few years ago. But he was one of the first people to talk about quantum hardware and quantum algorithms, and he spent his whole career doing that, perhaps before his time. But in 1981, there was a conference where both Paul and Richard Feynman, who many of you know because he's a Nobel Prize winner in physics, suggested that quantum computers could be better than classical computers at modeling quantum phenomena. And if you want to know a little bit more about the different steps in what happened in quantum computing, first of all, Wikipedia is a good source, which is very detailed and very, very, very thorough. But you may want to read something that's a little popular reading, which is in this article by Ed Jen at lifescience.com. So David talked about Peter Shor's work. So in terms of quantum algorithms, in 1994, Peter Shor, who's now at MIT, at that time at TNT Bell Labs, I believe, designed an algorithm, a quantum algorithm for factoring numbers into primes. Okay? Here's the reason why that was an important development. Widely used cryptographic protocols that we use, for example, that every time when you use a credit card and so on, the information is hidden from anybody who might want to abuse it. So those cryptographic protocols are based on the hardness of factoring very large numbers using classical computers. Okay? But Shor's algorithm, which factors numbers into primes, could be used to break these protocols when quantum computers become sufficiently powerful. And that, of course, generated a huge amount of interest from both governments and from industry, as these charts will show. So these charts are showing you how much research funding has been spent on non-classified quantum technology research as of 2015 in millions of euros. Right? So this plot is from The Economist. And you can see the United States is here, China is here, here is Europe, and so on. In fact, these numbers are, 10 years, or 2015, so about almost 10 years old. China has, for example, announced a $10 billion dollar investment in a quantum computing center. Of course, companies immediately followed suit. So IBM, Google, all this, you can read the numbers. So again, very different kinds of architectures based on different kinds of quantum phenomena and so on. And of course, companies like Volkswagen, Daimler, Airbus, financial companies and so on. And some of the companies, or representatives from some of these companies are here, so you'll get a chance to hear from them. In terms of publications, here are the top 6 countries. Here are the total publications, US, China, and so on. And what this chart is showing is that how much international collaboration is happening. So there are 4,500 publications. Again, this is from 2004 to 2013, so it's pretty old data. But this is the best data that I could find very quickly. So you can see that most of these, out of the almost 5,000 publications, about 4,500 publications are from the United States, are only for researchers within the United States. So actually, a lot of this effort is happening purely, within the boundaries of a nation, not so much internationally. But the point I want to make is not about that. The point I want to make is that all of this has been going on, and unfortunately, applied mathematicians have not been at the table. And so this is an opportunity for us to make a difference in this field by bringing the tools, the methodologies, the knowledge that we have to both help develop the field of quantum technologies, but also, as we look at these problems, more interesting problems come in that we could work that will enrich applied mathematics itself. So, in terms of the participants here, we have experts in applied mathematics, computer science, physics, chemistry, engineering, and others as well. We have participants from universities, national labs, and industry. We have people who are experts in quantum computing, and we're going to learn from them. But also, many of you are interested about quantum and want to learn about it, and so you're here to hear from them and to listen to these talks and to interact and have opportunities to discuss, perhaps build partnerships, and so on. And of course, there are a few quantum agnostic people might as well be here. Okay. And everybody brings different skills, perspectives, and ideas. So please don't feel that, I don't have the expertise. I'm not a quantum expert, so I can't contribute. But you can. You really, by bringing your expertise and your interests and your experience, we can all, have a good discussion over the next 3 days and lead to some real progress. We also have specialists from education, and that is a very important component also of the work that we need to do, because one of the most important things that we do in this meeting is the fact that we are making quantum computing a little more accessible to a larger group of people, applied mathematicians at various stages in their careers. And we hope that you will go back to your institutions and be change agents who will continue to have this conversation in your institutions. All right, so here are some big questions. So later on, we'll have a complete list of questions that we would like you to think about and so on. But I just wanted to kind of paint a broad picture. So how might applied mathematics advance quantum technologies through approaches that have not been considered so far, simply because people with our training and expertise have not been at the table? How might, and vice versa, as I said, how might research in quantum technologies enrich applied mathematics by bringing new problems and new ideas? In terms of the workforce, how do we create an innovative and diverse workforce that can bring mathematical ideas to multidisciplinary research in quantum technologies? And then how can we lower the knowledge barrier? This is an important question, because I think for many people who say, yeah, I'd be happy to work in quantum computing, but I don't want to spend the time reading 3 textbooks that have already been written on this field, right? So how can we lower the knowledge barrier so that more applied mathematicians can participate in this work? In terms of partnerships, how can we participate in partnerships involving academia, national labs, and industry to advance quantum technologies? And what do we hope to accomplish? We want to make more mathematical scientists aware of the demand for expertise in quantum research and in articulating areas and problems where they can contribute. We want to increase the participation of researchers in mathematical sciences in the quantum technologies revolution to accelerate its research and development. We want to provide a seeding ground for partnerships and collaborations with mathematical scientists with physicists and computer scientists and engineers from these different domains. We want to make some recommendations to federal research and development agencies, particularly NSF, which has funded us so graciously, towards support of research and education. And also, hopefully, what will come out is from our discussions will be some sort of a document that, again, could be made accessible and available to other applied mathematicians so they can be better informed about quantum computing and to get involved in this research. So that's all I have to say. Let's get to work. Thank you.